Module 3, Lecture B, Training Loop Design. By the end of this lecture, you will be able to implement a standard PyTorch training loop that iterates over DataLoader batches and updates model parameters. Add evaluation and metric computation to the training workflow without leaking gradients or mixing modes. And handle device placement and optional mixed precision to improve performance while maintaining correctness. Training epoch loop, iterating over batches. During a training epoch, we process data in small batches instead of feeding the entire dataset to the model at once. This is necessary because handling all the data together would exceed memory limits on typical GPUs and CPUs. By iterating over batches one after another, the model updates its parameters gradually while keeping memory and computation demands manageable. This batch-based training loop is a practical way to control resource usage and still allow the model to learn effectively. The data loader is a key part of training, serving as an iterator that feeds the model batches of inputs and targets, such as images with labels or text with next word predictions. At the start of each epoch, it usually shuffles the data to reduce overfitting. During training, each batch is moved to the computing device, passed through the model, used to compute the loss, and then used to update the model parameters. This simple repeated pattern underlies deep learning workflows, from small experiments to large-scale systems with millions of examples per epoch. When training a model to predict housing prices from features like location, size, and age, each batch should contain a diverse mix of houses so the model can learn a broad, accurate mapping from features to prices. If batches are mishandled, for example by skipping or repeating them, the model can become biased towards certain data and perform poorly. Proper batch iteration ensures every data point contributes to learning, keeps the computational load manageable, and helps maintain stable, reproducible training. This stability and reproducibility are essential for debugging and reliably deploying models in practice. Python code, iterating over batches. This script demonstrates how to iterate over training data in batches using TensorFlow. It simulates a typical batch training loop where data is processed in chunks rather than all at once. The main idea is to help you feel the rhythm of how multiple batches make up a single epoch during training. By focusing on this flow, you can better understand how models see the data repeatedly over several epochs. The commented line is a command to install TensorFlow version 2.20.0, usually run in a terminal or notebook. Its purpose is to make sure the script uses this specific version of TensorFlow. This helps maintain compatibility and prevents problems that might occur if newer versions change or remove features the script depends on. We begin by importing the operating system library, so the program can interact with the computer's operating system. We also import the random library, which lets us generate random numbers, for example when we need random seeds. Finally, we import the numerical computing library, NumPy, which we will use to create and work with arrays and perform efficient numerical calculations. We begin by importing TensorFlow, a library used for machine learning and deep learning, so we can build and train models. After importing it, we check which version is installed. Knowing the version is important because different versions can have different features or syntax, and this helps us make sure our code is compatible and runs as expected. To make our experiments reproducible, we set a fixed seed value for all the random number generators we use. We first set the seed for Python's built-in random system, then for NumPy's random system, and finally for TensorFlow's random system. Using the same seed across these libraries ensures that every time we run the code, the random values and TensorFlow operations behave the same way. This consistency allows us to repeat experiments and reliably obtain identical results. This line displays the version of TensorFlow currently in use, allowing you to quickly verify that the correct library version is installed and accessible in your script. Confirming the version helps ensure compatibility with the rest of your code. It is especially important when certain features or behaviors depend on a specific TensorFlow release. We first ask TensorFlow which devices it recognizes so we can see whether a physical GPU is available for acceleration. We then convert this information into a simple true or false check for GPU presence. Based on the result, we set the device name to GPU when one is available, or fall back to CPU when it is not. This lets us clearly indicate to the user which hardware will run the computations and helps ensure performance is optimized. The code prints a message to tell the user which device is being used for computations. It relies on a device name that was set earlier based on whether a graphics processor is available. This lets the user know if the program will run on a graphics processor or on the main processor. Understanding this helps the user anticipate how fast the computations might run. We start by creating a small synthetic dataset for a regression task. We choose 64 samples and 3 features. Then generate a matrix of random numbers with these dimensions using a numerical library. Finally, we convert this matrix to the float32 data type, so it will work smoothly with TensorFlow operations later on. We define the true weights of our linear model as the 3 values 2, -1, and 0.5, which act as the coefficients for the features in our synthetic dataset. To generate target values, we multiply the feature matrix by these weights and then add a small constant bias of 0.1. This process creates targets that follow a simple linear relationship, which we will use to train and evaluate the model. Before building the dataset, the code first verifies that the input features and target values have the correct shapes. It checks that the feature data forms a matrix whose dimensions match the number of samples and the number of features. It also confirms that the target data forms a vector with 1 value per sample. These checks help ensure the data is consistent and valid before any further processing. We begin by choosing a batch size of 8, which controls how many samples are processed together in each training step. Then we build a TensorFlow dataset from our input features and target values using a method that slices them into aligned pairs. This dataset is organized for efficient batch processing, so the model can work through the data in small, manageable chunks. This approach is especially important when training on larger datasets, where processing everything at once would be impractical. We begin by shuffling the dataset so the samples are mixed, which helps reduce bias during training. The shuffle step uses the full number of samples as the buffer size, so all data points are included, and a fixed seed is set so the shuffling can be reproduced. After shuffling, we divide the data into batches, where each batch contains a number of samples equal to the chosen batch size. This batching makes training more efficient by letting the model process smaller, manageable chunks of data at a time, and can help it converge faster. We build a simple dense regression model using the Keras interface in TensorFlow as a sequential stack of layers. First, we define an input layer whose shape matches the number of features in our dataset, so the model can receive the data correctly. Then we add a dense layer with a single output unit that learns a linear transformation from the inputs to one predicted target value. With these layers in place, the model is ready to be trained on a regression task. We use TensorFlow's stochastic gradient descent optimizer with a learning rate of 0.1 to update the model's weights during training and reduce error. To measure this error, we define the loss function as mean squared error, which is the average of the squared differences between predicted and actual values. This loss value indicates how well the model is performing and guides the optimizer in adjusting the weights to improve future predictions. We set the training to run for one epoch, meaning the model will pass through the entire dataset a single time. Before training begins, we print a message that announces the start of training and states the number of epochs. This simple message helps track progress and clarifies the scope of the training session. We run a training loop over the chosen number of epochs, which is 1 in this example. At the start of each epoch, we set the total loss to 0, so we can accumulate how much loss occurs during that epoch. We also set a batch counter to 0 to track how many batches we process. By the end of the epoch, these values let us compute the average loss by dividing the total loss by the number of batches. We process the dataset one batch at a time in a loop, and in each step, we split the batch into input features and target values. This lets us handle each batch separately and work with smaller, more manageable chunks of data. We also increase a batch counter during each iteration to track how many batches have been processed. This approach helps organize and monitor the training process across the entire dataset. Before each batch is processed during training, the code checks that the number of samples does not exceed the predefined batch size. It verifies that the number of rows in both the input features and the target labels is less than or equal to this limit. This assertion keeps the batch size consistent and manageable for the model. It also helps detect unexpected batch size issues early, before the forward pass in the training loop. We use TensorFlow's gradient tape to record the operations needed for automatic differentiation during training. Within this context, we pass the current batch of input data through the model in training mode to generate predictions. We then compute the loss by comparing these predictions to the true target values using the mean squared error. This recorded computation is what later allows us to calculate gradients and update the model's weights. In this step, we use TensorFlow's automatic differentiation to compute how the loss changes with respect to each trainable variable in the model. These computed values are the gradients. We then pair each gradient with its corresponding variable and pass them to the optimizer. The optimizer uses this information to update the model's weights so that the loss is gradually reduced over time. We add each batch's loss to a running total for the whole epoch, so we can track how the loss accumulates as we process the data. At the end of the epoch, this running total lets us compute the average loss across all batches. We also convert the loss value to a standard Python floating point number to keep it compatible with other operations that expect this data type. The code checks whether the current batch index is less than 2, meaning it is one of the first 2 batches in the epoch. For these early batches, it prints the current epoch number, the batch number, and the loss value. This provides quick feedback on how training is starting out and helps confirm that the model is learning as expected in the initial steps. To find the average loss for an epoch, we divide the total loss accumulated over all batches by the number of batches processed. This value tells us how well the model performed on average during that entire epoch. We then report this average loss, rounded to 4 decimal places, together with the epoch number. This provides a clear, concise summary of the model's training progress over time. This script shows a simple batch training loop in TensorFlow for a basic regression task. It creates a synthetic dataset where random inputs are mapped to targets by a linear rule, then shuffles and batches the data. A small neural network with one dense layer is trained using stochastic gradient descent and mean-squared error loss. For each batch in a single epoch, the script computes predictions, evaluates the loss, and updates the model weights using gradients, printing the loss for the first 2 batches and the average loss at the end. It also checks whether a GPU is available and reports which device is used, highlighting how batch processing works within an epoch during training. Forward pass and loss. After loading a batch of data and moving it to the correct device, the next step is the forward pass, where the model turns inputs into predictions. In this step, an image classifier converts images into class scores, and a language model predicts the next word. The data flows through each layer in sequence, with each layer transforming the information and passing it on. The final output reflects the model's current understanding and provides the basis for evaluating how well it is performing. After the model makes predictions, we compute a loss value that measures how far those predictions are from the true targets. This loss function converts the model's performance into a single number that we want to minimize. In different applications, such as medical diagnosis or recommendation systems, the loss can be designed to reflect how serious different kinds of errors are. This single loss value is crucial because it guides how we update the model's parameters through backpropagation, and we usually average it over a batch of data to make training more stable. During training, the forward pass and loss computation should be treated as a single step because together they define what the model is trying to learn. The model must be set to training mode so that components like dropout and batch normalization behave correctly. The loss is not just for monitoring, it directly drives the gradients used in the backward pass. A lower loss means the model's predictions, such as steering and autonomous driving, are more accurate, while a higher loss signals poor performance. Repeating this process over many epochs gradually refines the model's parameters and improves its overall behavior. Python code, forward pass, and loss. This script shows how a forward pass and loss calculation work in a simple training setup. It uses TensorFlow to imitate the core training logic without focusing on full model details. The main goal is to illustrate how predictions are produced for batches of data and how these predictions are turned into a single scalar loss value. This helps clarify the basic flow of data and loss computation during training. The line that starts with an exclamation mark is a command to install TensorFlow version 2.20.0. It is usually run in a Jupyter notebook or similar environment. The purpose is to make sure that this exact TensorFlow version is available so the script can run correctly. This helps ensure that the code that follows is compatible with the TensorFlow features and functions it depends on. We begin by importing 3 key Python modules that support our work. The operating system module lets the script interact with the system, for example, to work with files or environment settings. The random module provides tools for generating random numbers, which we can use for tasks like shuffling or sampling data. Finally, we import the numerical computing library NumPy, which offers efficient operations on large, multidimensional arrays and matrices. Together, these imports provide the basic tools needed for data manipulation and randomization in the script. We begin by importing TensorFlow, a main library used to build and train machine learning models. Within TensorFlow, we use Keras as a high-level interface that makes creating neural networks easier. We also import the layers tools from Keras, which provide the basic components for building the network structure. These imports prepare all the essential tools we need to define and train our model in the rest of the program. We set a fixed seed value so that all random operations in our code give the same results every time, which is important for reproducible machine learning experiments. This involves setting the seed for Python's built-in random number generator, then for NumPy's random generator, and finally, for TensorFlow's random generator. Doing this ensures that things like randomly generated numbers and initial neural network weights are consistent across runs. With aligned seeds, the entire pipeline behaves predictably, making debugging and comparing results much easier. The code first asks TensorFlow to list all available physical GPU devices, then checks whether this list is empty or not. If at least one GPU is found, it sets a flag to indicate that a GPU is available. Otherwise, the flag is set to false. Based on this flag, it chooses the device type as either GPU or CPU. This logic allows the program to automatically use GPU acceleration when possible, which can greatly speed up deep learning training and inference. The script first reports the TensorFlow version in use, so you can confirm exactly which version is running for compatibility and debugging. It then reports whether the model is using a GPU or a CPU. Knowing the device type is important because it tells you what computational resources are available. This is especially relevant for performance since running on a GPU can greatly speed up training and inference compared to a CPU. We create a small synthetic dataset for a classification task by choosing 3P settings. We set the total number of samples to 64, so the dataset has 64 data points. Each data point is described by 20 features, meaning it has 20 attributes. Finally, we define 3 classes, so the model will learn to distinguish among 3 different categories. We begin by using a numerical library to create random data for a classification task. First, we generate a 2-dimensional array of random feature values, with one dimension for the number of samples and the other for the number of features, and we store these values as 32-bit floating point numbers so they work smoothly with TensorFlow. Next, we create random integer labels for each sample, choosing values from 0 up to 1 less than the total number of classes. Together, these steps simulate a multi-class classification dataset with random inputs and corresponding class labels. Before building the dataset, the code first checks that the feature matrix has the expected shape, with 64 samples and 20 features. It also confirms that the label array contains 64 samples. These checks verify that the data dimensions are correct and consistent. By catching any mismatches early, they help prevent errors later during model training. We begin by choosing a batch size of 8, which controls how many training samples are processed together in each step. Then we build a TensorFlow dataset from our input features and labels. This dataset structure lets us handle the data efficiently and iterate over it in batches during training. The dataset is shuffled using TensorFlow's shuffle method to randomly rearrange the data points and remove any order that could bias trading. The buffer size is set to the total number of samples, so the entire dataset is included in the shuffle. A seed value is provided so that this random shuffling is deterministic, meaning it produces the same shuffled order each time the code is run. This makes the training process both less biased and easier to reproduce. The dataset is split into smaller groups called batches, each with a set number of samples. In TensorFlow, this is done using a batching method that takes the desired batch size as input. Batching is important because it helps use memory more efficiently and supports parallel processing during training. As a result, it is a key step in preparing data for machine learning models. In this example, we build a simple dense neural network model using Keras in a sequential way, adding one layer after another. The model begins with an input layer that accepts data with a specified number of features. It then includes a dense layer with 16 units and a ReLU activation function to introduce nonlinearity. Finally, it ends with a dense output layer whose number of units matches the number of classes and uses a softmax activation function to produce class probabilities for classification tasks. We configure the model by choosing an optimizer and a loss function. The optimizer is stochastic gradient descent with a learning rate of 0.1, which updates the model's weights during training to reduce the loss. For the loss function, we use sparse categorical cross-entropy, which is appropriate for multi-class classification when the labels are integers. This loss measures how well the predicted class probabilities match the true labels. We start training by running one epoch and focusing on the forward pass, where we manually loop over the dataset. For each batch, we compute the model's predictions and the corresponding loss values. This step is essential for training a neural network because it shows how well the model is performing on the data. Doing it manually also lets us closely observe and control the training dynamics and better understand how the model learns. We process the dataset one batch at a time, and in each step, we split the batch into input features and labels. We then check that the feature data has the expected number of columns and that the labels form a one-dimensional array. These defensive checks help us quickly detect and diagnose any unexpected problems in the data before moving on. We begin by creating a gradient tracking context using TensorFlow's gradient tape, which records all operations on tensors, so we can compute gradients later. Within this context, we run a forward pass of the model on the current batch of input data. The model uses these input features to generate predictions called logits while operating in training mode. This forward pass is essential because it provides the outputs needed to calculate the loss and update the model's weights. In this step, we compute the loss for the current batch using the sparse categorical cross-entropy loss function. This function takes the true labels and the model's predicted logits and produces a single scalar value. That value measures how well the predictions match the actual labels. It is essential for training because it quantifies the error the model must minimize during optimization. The code uses TensorFlow's gradient tape to compute how the loss changes with respect to each trainable parameter in the model. The gradient tape records the operations during the forward pass. Then its gradient function calculates the derivatives of the loss with respect to these variables. These gradients are then used to update the model's parameters during training. The optimizer uses the calculated gradients to update the model's parameters, adjusting the weights to reduce the loss. By moving the parameters in the direction indicated by the gradients, the model effectively learns from the data. Each gradient is matched with its corresponding trainable variable so that every parameter is updated correctly according to its contribution to the loss. The code checks whether the current loop step is less than 3, so it only reports the first few iterations, which is useful for debugging and seeing the model's initial behavior. When this condition is met, it prints the step number and the batch loss. The step number is converted to an integer, and the batch loss is converted to a float using a numerical library, so the values are easy to read. This gives a quick snapshot of how the model is performing during the early training steps. To make predictions on a single batch without computing gradients, we first get the next batch from the dataset iterator. This batch provides both the input features and their corresponding labels. With these in hand, we can run the model on the inputs and compare its predictions to the labels. This lets us evaluate the model's performance on that batch without changing or updating its parameters. To evaluate a trained model without changing it, we turn off gradient tracking by setting the model to evaluation mode before running data through it. This prevents any updates to the model's parameters while it processes the input. The model then outputs predicted probabilities for each class, which we can use to judge how well it performs. In this way, we assess its predictions without affecting the learned weights. This code computes the evaluation loss for a batch of data by applying the sparse categorical cross-entropy loss function. It compares the true labels from the first batch with the model's predicted probabilities. The resulting loss value is then converted into a standard numerical format using a numerical library, making it easy to use for further analysis or display. The script reports the evaluation loss for the first batch of data by converting the loss value to a floating point number and printing it with a clear message. This gives a quick snapshot of how well the model performs on that initial batch after a training epoch. By examining this early loss value, you can gauge the model's accuracy and identify whether it may need further improvement. This script shows a simple example of running a forward pass and computing loss in TensorFlow. It creates a small synthetic dataset with multiple features and 3 classes, then shuffles and batches the data. A basic neural network with one hidden layer using ReLU and an output layer using softmax is trained with stochastic gradient descent and sparse categorical cross-entropy loss. During a single training epoch, the script iterates over the batches, makes predictions, computes the loss, and updates the weights using gradients, printing the loss for the first few steps. It then evaluates the trained model on the first batch without tracking gradients and prints the evaluation loss to show its performance after this brief training. Backward pass and update. After computing the loss for a batch, the next step is to send this error signal backward through the network so the model can learn. First, clear any existing gradients in the model's parameters, because most frameworks accumulate them and leftover values would interfere with learning. Then run the backward pass on the loss, which makes the framework move in reverse through the computation graph, and use the chain rule to find how each parameter contributed to the error. In effect, this process measures how small changes in each weight would change the loss for the current batch, regardless of whether the data is images, audio, or transactions. After computing gradients for all trainable parameters, the optimizer updates the model to reduce future loss. It looks at each parameter's gradient and changes the parameter value according to its update rule, which may simply scale the gradient or adapt the learning rate. In this step, learning becomes concrete because the model's weights are modified using information from the current batch of data. For example, in a medical imaging model, weights that help distinguish different tissue types are adjusted so the model becomes more accurate on future scans. Over many such small updates, the model's performance improves significantly. In training loops, the backward pass and parameter updates depend directly on how batches are organized, because each batch provides only a partial view of the model's performance. The gradients you compute reflect just that batch, so the order of operations is critical. You must clear old gradients, run the forward pass, and compute the loss, perform the backward pass, and then update the parameters before moving on to the next batch. In large real-world systems, such as recommendation models, this cycle repeats many times, and the model's reliability depends on strictly following this sequence, so each batch contributes accurate gradient information. Python code, backward pass, and update. This lesson walks through a simple training loop with a special focus on how the backward pass works and how model parameters are updated. You will see how gradients are computed and then used to adjust the weights during training. To get the most benefit, run the script in an interactive environment like Colab so you can follow each step as it executes. The script begins by installing PyTorch along with its vision and audio libraries to make sure all required tools are available. This setup step is especially important in new or isolated environments, such as a fresh Google Colab session. By installing these libraries first, you ensure that all components needed to build and train neural networks are present. This prevents the rest of the script from failing due to missing dependencies. We begin by importing 3 standard library modules: OS, Random, and Math. The OS module lets the script interact with the operating system, which is useful for working with files and directories. The Random module generates random numbers, for example, when we need randomness or want to set a seed for reproducible results. The Math module provides common mathematical functions and constants that support various calculations in the script. To begin working with neural networks in PyTorch, we first import the main PyTorch library. We then import the neural network module, often called NN, which provides the building blocks for defining layers and models. Finally, we bring in the optimizer module, called Optim, which offers algorithms to update model parameters during training. Together, these imports prepare the environment for creating and training a neural network model. We begin by printing the current PyTorch version, so we can confirm exactly which release we are using. This is important because different versions may include different features or behave in slightly different ways. Seeing the version number helps us quickly verify that our environment matches what we expect. It also makes troubleshooting easier if we run into compatibility or debugging issues later on. We begin by setting a fixed random seed using the random library, so that any random operations in our code always produce the same results. This makes our experiments reproducible, meaning we can reliably repeat them and get identical outcomes. It is also important for debugging because consistent behavior helps us track down and fix problems more easily. We set the random seed in PyTorch using the manual seed function with 0 so that the random numbers it generates are the same every time the code runs. This makes the results reproducible, meaning we can reliably get identical outcomes from the same experiment. Reproducibility is important because it makes debugging easier and allows fair comparison between different runs or models. This code chooses which computing device to use by checking if a CUDA-capable GPU is available in PyTorch. If a GPU is found, it sets the device to use that GPU. Otherwise, it falls back to the CPU. This way, the model and data run on the fastest available hardware, improving performance during training. This code prints a message showing which device will be used for training. It first checks whether a graphics processing unit is available and uses it if possible. If no graphics processing unit is found, it falls back to using the central processing unit. Choosing the graphics processing unit when available is important because it can greatly speed up the training process. We begin by creating a very small synthetic regression dataset with 64 data points. This limited size keeps the example simple and fast to run. Using such a compact dataset lets us concentrate on understanding how the training loop works without the extra complexity of managing a large amount of data. To prepare our dataset, we first generate input features by creating a sequence of evenly spaced numbers between -1 and 1. This sequence serves as our input data. We then add an extra dimension to this one-dimensional sequence so that it becomes a two-dimensional tensor. This step is necessary because the linear regression model expects inputs with 2 dimensions, and this format ensures the data is compatible with the model. In this regression task, we define the target values using a simple linear rule. For each input feature, we multiply it by 3 and then add 0.5. This creates a basic linear relationship between the input and the target. The model is then trained to learn and reproduce this relationship from the data. The input features are moved to the computing device chosen earlier, which is a graphics processor if one is available. or otherwise a central processor. This step makes sure the data is on the same device as the model. Doing so improves performance and avoids compatibility issues during training. The target data is moved onto the chosen computing device, such as a graphics processor or the main processor, depending on what is available. This step makes sure the data and the model are on the same device. As a result, the training process can run more efficiently and avoid slow transfers between different devices. In this example, we build a simple linear regression model using PyTorch's neural network tools. The model has just one linear layer, which applies a basic linear transformation to the input data. It is set up to take a single input feature and produce a single output feature, so it effectively represents a straight line. This kind of model is commonly used for basic regression tasks where we want to predict a continuous value from one input variable. The model's parameters are being moved to a specific device, such as a GPU or CPU, so that all computations happen in the same place as the data. This alignment is essential for the model to run correctly and efficiently. Placing the model on the chosen device ensures compatibility between data and computations, and is especially important when using a GPU to take advantage of faster, accelerated processing. We use the mean squared error loss function from PyTorch's neural network module to evaluate our model's predictions. This loss measures the average of the squared differences between the predicted values and the true target values. Because it squares the errors, larger mistakes are penalized more heavily. This makes it a common and effective choice for training regression models to produce more accurate predictions. We use a stochastic gradient descent optimizer from the PyTorch optimization module to update the model's parameters during training. By passing in the model's parameters, we tell the optimizer which values to adjust. We also set a learning rate of 0.1, which controls how large each update step is. This configuration is essential for guiding the model to reduce the loss function effectively. In this step, the input features and target values are combined into a single tensor dataset. This PyTorch utility links each data example with its corresponding label in one unified dataset object. Creating this paired dataset is necessary so it can be passed to a DataLoader. The DataLoader then takes care of batching and shuffling the data during training. We use a DataLoader to iterate over the dataset in small mini batches, which makes model training more efficient. Here, the batch size is set to 8, so each batch contains 8 samples. We also turn on shuffling, so the data order is randomized at the start of each training epoch. This helps prevent the model from picking up unwanted patterns based only on the original order of the data. We set the training loop to run for 5 epochs, meaning the model passes through the entire dataset 5 times. Each pass lets the model adjust its internal parameters based on the data. By repeating this process across multiple epochs, the model gradually improves its ability to make accurate predictions. We start a loop that runs through each training epoch, meaning each full pass over the dataset. This repeated exposure to all the data is essential for the model to learn effectively. By iterating for a set number of epochs, the model gets multiple chances to adjust its parameters and gradually improve its predictions based on the training data. Setting the model to training mode prepares it to learn during the current epoch. This step makes sure that layers which behave differently during training, such as dropout and batch normalization, are configured correctly. In training mode, these layers update their internal parameters based on the incoming data. As a result, the model is properly set up to adjust its weights and improve performance in this phase. We start by setting a variable called running loss to 0, so it can track the total loss across all mini batches in one training epoch. As each mini-batch is processed, its loss is added to this running total. Resetting it to 0 at the beginning of every epoch keeps the calculation separate for each pass through the data. This helps us accurately monitor how the model's performance changes over time during training. In this part of the code, we loop over the mini-batches produced by the DataLoader. And each time we get a small batch of input features and their target values. Working with these smaller chunks makes it possible to train efficiently on large datasets. As we iterate through the mini-batches, we can run forward passes, compute the loss, and perform backpropagation in a way that uses memory and computation more effectively. We make sure each batch of data is sent to the correct computing device, either a graphics processor or the main processor, depending on what is available. This step keeps the computations consistent and reliable. It also allows the program to take advantage of hardware acceleration when a suitable device is present. We move the target batch to the same device as the inputs, so they are both processed on the same hardware, whether that is a CPU or a GPU. This alignment is necessary because many tensor operations require all inputs to be on the same device. Keeping them together on one device ensures efficient computation and prevents device mismatch errors during training or evaluation. Before running the forward pass, the code first checks that the input batch has the expected shape. It verifies that the second dimension equals 1, meaning each sample contains only a single feature. This simple assertion acts as a safeguard, catching unexpected changes in data shape early. By enforcing this condition, it helps prevent shape-related errors during model training. In this part of the code, we reset the gradients that were computed in earlier iterations. This is necessary because in PyTorch, gradients are added up by default instead of being replaced. If we did not clear them, new gradients would stack on top of old ones and cause incorrect parameter updates during optimization. By calling the method that sets all gradients to 0 before each backward pass, we ensure that learning is based only on the current batch of data. In this part of the code, we run a forward pass through the model using the current batch of input data to produce predictions. The model relies on its current parameters to compute these outputs. We will later compare these predictions with the true target values to calculate the loss. This step is essential because it shows how well the model is performing before any parameter updates are applied. In this step, we compute the loss by comparing the model's predictions with the true target values. We use the mean squared error loss, which is the average of the squared differences between predicted and actual values. This loss value tells us how well the model is performing. During training, we use it to adjust the model's parameters so that this error is reduced over time. The backward pass is the stage where learning actually occurs. During this step, the loss backward method computes how the loss changes with respect to each model parameter. These computed values are called gradients, and they indicate how much each parameter contributed to the error. The optimizer then uses these gradients to adjust the parameters in the direction that reduces the loss. The optimizer step is the stage where the model's parameters are updated using the gradients computed during the backward pass. It applies these gradients to adjust the parameters in a way that reduces the loss function. By repeating this process over many steps, the optimizer gradually refines the model's weights and improves its performance. We update the running loss by adding the contribution from the current batch. To do this, we first convert the loss value from a tensor to a regular Python number. Then we multiply this loss by the number of samples in the batch, obtained from the batch input size, to get the total loss for that batch. This total is added to the running loss so that later on, we can easily compute the average loss over all samples. To find the average loss for an epoch, we take the running loss, which is the total loss accumulated over all samples in that epoch, and divide it by the number of samples. This calculation gives the mean loss for the epoch. The mean loss summarizes how well the model is performing on average across all data points. At the end of each training epoch, the program prints a short summary line that includes the epoch number and the average loss for that epoch. This summary gives you a quick snapshot of how the model is performing. By watching how the average loss changes over epochs, you can easily track whether the model is learning effectively over time. During evaluation, we run the model on the full dataset without computing gradients. We do this by using a context that temporarily turns off gradient tracking. This is helpful because, unlike training, evaluation does not need gradients. As a result, we save memory and speed up computation while still getting the model's outputs for assessment. Switching the model to evaluation mode is essential when performing inference. This change tells the model to use its evaluation behavior instead of its training behavior. In particular, it fixes how layers like dropout and batch normalization operate, so they no longer act in a training-specific way. As a result, the model's predictions become stable and consistent, allowing for an accurate assessment of its performance on new, unseen data. After training, the model is used to generate predictions for the entire dataset. The input data is passed through the model to produce output values for each example. This step is essential because it provides the predicted results needed to evaluate how well the model performs on the dataset. The code computes the final mean squared error by comparing the model's predicted values with the actual target values. It uses the mean squared error loss function to measure how closely the predictions match the targets. The resulting error value is then converted into a regular Python number, so it is easier to read and use in later steps. To wrap up, we calculate and print the mean squared error on the tiny dataset to see how well the model has learned. We round the final loss value to 4 decimal places, so the result is easy to read and interpret. This final number serves as a concise summary of the model's performance after training. This script shows a basic training loop in PyTorch for a simple linear regression problem. It creates synthetic data where the targets are 3 times the inputs plus 1/2, then defines a linear model with 1 input and 1 output. The model is trained for several epochs using mean square error as the loss function and stochastic gradient descent to update the weights through backpropagation. After training, the script evaluates the model on the full dataset without computing gradients and reports the final mean squared error, allowing you to see how the loss decreases as the model learns. Evaluation and metrics. Training versus evaluation modes. In neural networks, it is important to switch correctly between training mode and evaluation mode. During training, the model updates its parameters based on data, while during evaluation, it should only make predictions without further learning. Certain layers, such as those that drop units to reduce overfitting or normalize activations, behave differently in each mode. If you validate while still in training mode, your metrics will be unreliable, and if you train while stuck in evaluation mode, the model will not learn properly. Managing these modes correctly ensures the model behaves as expected in real-world use. In a training loop, it is essential to switch the model between training and evaluation modes at the correct times. Keep the model in training mode while computing loss and updating parameters so that all learning behaviors are active. Before running validation or testing, switch to evaluation mode so layers behave deterministically and use stable statistics. This ensures the model's behavior during evaluation matches real-world use and avoids unpredictable outputs. When computing metrics like accuracy or precision, it is essential to keep training and evaluation modes separate, so the results reflect the model's true behavior rather than training time randomness. If you forget to switch modes, the metrics can be misleading, and may cause poor choices about early stopping or which model to deploy. In real-world settings such as energy forecasting or fraud detection, this can lead to costly mistakes. By consistently using the correct mode, you obtain reliable metrics, make fair model comparisons, and keep deployed performance aligned with offline evaluations. Python code, training versus evaluation modes. This script demonstrates how to switch between training and evaluation modes while keeping the handling of metrics clear and consistent. It uses TensorFlow in a way that imitates how PyTorch manages these modes. The main goal is to track and report metrics correctly without mixing them with gradient computation or optimization steps. This separation helps you focus on evaluating model performance independently from the training process. The line with the exclamation mark is a command that installs TensorFlow version 2.20.0. Using this exact version, make sure the script runs with the library it was designed for. This helps prevent compatibility problems that could occur if a different TensorFlow version were used. We start by importing 3 key libraries. The operating system library lets us work with the system environment and files. The random module gives us tools to generate random numbers for things like random data or seeds. Finally, the numerical computing library NumPy allows us to work efficiently with arrays and perform fast mathematical operations. We start by importing TensorFlow, a powerful library for machine learning and deep learning. Within TensorFlow, we use Keras as a high-level interface that makes it easier to build and train neural networks. We then bring in the layers module from Keras, which provides key components like convolutional and dense layers. With this setup, we can efficiently construct and manage deep learning models. We begin by setting a seed value of 42. So that any random operations give the same results every time we run the code, which is important for reproducibility. To do this consistently, we set the seed in the random library, then in the NumPy random number generator, and finally in TensorFlow's random operations. Using the same seed across these libraries makes our experiments deterministic and easier to repeat and verify. This line displays the version of TensorFlow currently in use. It provides a quick way to check which version of the library is installed. Knowing the exact version is important because different versions may behave differently. This helps with ensuring compatibility and makes debugging easier. The code uses TensorFlow to check whether any GPU devices are available by listing all physical devices of type GPU. It then converts this list into a true or false value, which is true if at least one GPU is found. Based on this result, it prints a message telling the user whether a GPU is being used for computations. This lets the user quickly confirm what kind of hardware is running their code. We start by loading a subset of the MNIST dataset, a standard collection of handwritten digit images used to train image processing models. This dataset is split into training data and test data. The training images and their labels are used to teach the model to recognize digits, while the test data is used afterward to measure how well the model has learned. Setting up this split is an essential first step in building the data pipeline for training and evaluating the neural network. The code limits the number of training samples to 2,000 to reduce the dataset size and speed up the training process. This smaller subset allows the model to run more quickly, making it easier to demonstrate how training works. By using fewer samples, the script becomes more practical for testing and debugging without having to process the full dataset. The code limits the number of test samples to 500. This restriction reduces the amount of data used during evaluation. As a result, the testing process runs faster and is easier to handle. This setup is mainly intended for demonstration purposes rather than full-scale evaluation. We limit the test set to 500 samples so evaluation is faster and easier to manage. For demonstration, we also restrict the training data to the first 2,000 samples so the model can train more quickly without using the full dataset. The training labels are reduced in the same way so they stay correctly aligned with the selected training inputs. To make evaluation faster, the code limits the size of the test dataset. It keeps only the first 500 test images and their matching labels. By working with this smaller subset, the evaluation runs more quickly. This approach is especially useful when you only need a quick demonstration rather than a full, time-consuming test. The code converts the training and test images to floating point values and scales all pixel intensities to lie between 0 and 1 by dividing by 255, the maximum value in an 8-bit image. This normalization step is important because it makes the data more consistent and easier for the neural network to process. As a result, the learning process becomes more stable and the model can converge more effectively during training. We add a new axis to the end of the training and test datasets to create a channel dimension. Convolutional layers in neural networks require inputs that include this channel information. By expanding the data in this way, we put it into the correct shape so the convolutional neural network can process it properly. Before building the model, the code checks that the number of training samples matches the expected amount by confirming the shape of the training data. It performs the same check on the test data to ensure those samples are also correctly selected. These shape checks help catch any mistakes in how the data was sliced. So problems are found early and the data is confirmed to be prepared correctly before model construction begins. We build a simple convolutional neural network in Keras as a sequence of layers. It starts with a two-dimensional convolutional layer with 8 3x3 filters using ReLU, taking 28 by 28 grayscale images as input, followed by a 2x2 max pooling layer to reduce spatial size. A dropout layer with a rate of 50% is added to reduce overfitting, and the result is flattened into a one-dimensional vector. This feeds into a dense layer with 32 ReLU units, and finally a dense output layer with 10 units and a softmax activation to produce class probabilities for the 10 MNIST digits. Before training, the model is compiled, which means we set up how it will learn and how its performance will be measured. We choose the Atom optimizer so it can adjust the model's weights during training. We use sparse categorical cross-entropy as the loss function, which is appropriate for multi-class classification when the labels are given as integers. We also track accuracy as a metric so we can see how well the model is correctly classifying the data during training and testing. The code starts a short training session for the model using a fit-style method with the training data and labels. The model trains for 2 epochs, so it passes over the entire dataset twice. It uses a batch size of 64, meaning it updates its weights after every group of 64 samples. The verbose setting is turned off, so no training logs are printed, keeping the process faster and less cluttered. We use a helper function to manually compute accuracy by first turning predicted probabilities into predicted classes, choosing the class with the highest probability for each sample. It then checks that these predicted classes have the same shape as the true labels so they can be compared correctly. Finally, it compares predictions to true labels, takes the average of correct matches, and returns this value as a floating point accuracy score. This provides a simple way to evaluate model performance without relying on built-in accuracy tools. We make the model trainable, so its weights can be updated. And in Keras, we simulate training mode by using the training argument. We then run the test data through the model with training set to true, which activates dropout and other behaviors specific to training. The model's output probabilities are converted into a numerical array, and we pick the most likely class for each example. Finally, we compare these predicted classes to the true labels to compute accuracy, which tells us how well the model performs when it is behaving as if it were still in training mode. To run the Keras model in evaluation mode, we first attach a placeholder evaluation attribute as a workaround, since Keras does not provide a direct evaluation method like some other frameworks. We then set the model's training flag to false, so that layers such as dropout and batch normalization behave as they should during evaluation. With this setting, we pass the test data through the model and convert the resulting output probabilities to a numerical array. Finally, we compute accuracy from these probabilities and the true test labels and store it as the clean evaluation accuracy, which reflects the model's performance in proper evaluation mode. This script first reports the model's accuracy when it is run in training mode, rounding the value to 4 decimal places and including a brief description. It then reports the accuracy when the model is run in proper evaluation mode, again rounded to 4 decimal places with a clear message. Comparing these two printed values highlights how the model's performance can differ between training and evaluation modes. To see how Keras evaluates a model, we use the model's evaluate function on the test data and labels. This evaluation step computes the model's loss and accuracy on the test set. We turn off extra output during this process so it runs quietly. Finally, we print the accuracy rounded to 4 decimal places to summarize how well the model performs in evaluation mode. This script uses TensorFlow to show the difference between training and evaluation modes in a neural network. It builds and briefly trains a simple convolutional model on part of the MNIST dataset, then measures accuracy in both modes. In training mode, dropout is active, which can change the accuracy compared to evaluation mode, where dropout is turned off. The script prints both accuracy values to highlight this behavior, and then uses the built-in Keras evaluation function to confirm the evaluation mode accuracy and ensure it matches the manual calculation. Safe inference with no grad. When evaluating a model, you should run inference without tracking gradients so the model does not keep learning during testing. In training, each forward pass is recorded to compute gradients. But if you forget to turn this off for evaluation, the system still builds computation graphs. This wastes memory, slows things down, and can cause subtle bugs if your code assumes no gradients exist. Using no gradient inference effectively puts the model in a read-only mode, where it produces outputs without recording any information from parameter updates. When evaluating models during training, it is important to turn off gradient tracking, especially for large validation sets or frequent checks. During evaluation, you are not updating the model's parameters, so you do not need to store computation graphs. Leaving gradients on wastes memory and can cause memory errors or force you to use smaller batch sizes. By disabling gradient tracking, you free up memory and make evaluations more efficient, allowing larger or more frequent validation runs without affecting the training process. Disabling gradient tracking during inference keeps training and evaluation clearly separated, which is especially important in complex workflows like medical imaging. For example, you might train on data from one hospital and evaluate on data from another to test how well the model generalizes. During this evaluation, you can compute metrics, generate visual explanations, and log predictions without changing the model's parameters or building unnecessary computation graphs. Consistently using this approach allows models to serve predictions continuously and compute metrics in real time while keeping their learned parameters stable and unaffected by inference tasks. Python code. Safe inference with no grad. This script shows how to safely run model inference using a no-gradient mode. It contrasts how gradients behave during training versus during evaluation. The goal is to compute evaluation metrics while preventing any training information from leaking. By disabling gradient tracking in evaluation, we keep the focus on measuring performance without affecting the learned parameters. The commented line is telling you to install the PyTorch and Torch Vision libraries, usually using a package manager like pip. These libraries are required because the code depends on them to run correctly. PyTorch and Torch Vision provide the core tools for working with tensors, building models, and handling data when creating and training neural networks in Python. Without installing them first, the rest of the code will not function as intended. We begin by importing a few standard Python libraries that provide essential tools for our script. The operating system library lets us work with files, folders, and other system features. The random library allows us to generate random numbers and make random choices, which is useful for simulations or creating sample data. The math library gives access to common mathematical functions and constants so we can perform more complex calculations. Together, these imports prepare the basic functionality needed for many computational tasks in Python. We start by importing key parts of the PyTorch library that we need to build and train neural networks. This includes the main PyTorch tools, the neural network module for defining layers, and the optimizer module for updating model weights during training. Together, these imports prepare the environment so we can create a neural network model and train it using PyTorch's built-in functionality. We begin by setting fixed random seeds using both the general random library and PyTorch so that any random operations behave the same way every time the code runs. This makes our experiments reproducible, meaning we can repeat them and get identical results. It also helps with debugging because controlling the randomness lets us more easily track down and understand the model's behavior. This code chooses whether to run computations on a graphics processing unit or on the central processor. It uses a built-in PyTorch check to see if a CUDA-capable graphics card is available. If one is found, it selects the graphics card for faster processing. Otherwise, it falls back to the processor. The result of this choice is stored in a device setting that will be used later to move all data and models to the selected hardware for efficient computation. We begin by checking and printing the current PyTorch version and the computing device being used, such as a graphics processor or a central processor. This step confirms that the environment is set up correctly and that the code will run on the intended hardware. Verifying this information is important for both performance and compatibility when working with PyTorch. TinyNet is a simple classification model built as a subclass of the standard neural network module in PyTorch. In its initialization method, it first calls the base class initializer to set up the underlying framework. It then defines a single, fully connected linear layer that takes the input dimension and the number of classes as arguments. This layer converts the input data into output scores that can be used to make classification predictions. The forward method describes how the model handles input data to produce predictions. It receives an input tensor and sends it through a fully connected layer. This layer applies a linear transformation to the input features. The result of this transformation is the model's output, which determines its predictions based on the given input. In this simple setup, we define three key settings for our classification problem. The input dimension is 4, so each data point has 4 features. We have 3 classes, meaning the model must choose among 3 possible categories. The batch size is 8, so during training or evaluation, we process 8 data points at a time. Together, these choices specify the basic structure of the data and how the model will handle it. To create a small batch of random training data, we first use a function that draws values from a normal distribution to generate input vectors with a chosen batch size and input dimension, simulating feature data. Then we use another function that produces random integers between 0 and the number of classes to form the labels, simulating target class assignments for a classification task. Together, these random inputs and labels provide a simple synthetic dataset for testing or demonstrating training procedures. We create a small batch of random validation inputs using a normal distribution, choosing the batch size and input dimensions to simulate feature data. Then we generate random validation labels by drawing integer class labels for each input based on the total number of classes. This random validation set lets us quickly check how the model performs on data it has not seen during training. During training and evaluation, all inputs and labels are first moved onto the available computing device, such as a CPU or GPU. The training inputs and their labels are placed on the same device so that learning computations run efficiently and consistently. The validation inputs and labels are also transferred to that device, so the model can be evaluated under the same hardware conditions. This setup ensures that all data used for both training and validation is ready for fast, unified processing on the selected hardware. We begin by creating a TinyNet model with the chosen input size and number of output classes and place it on the selected device, such as a CPU or GPU. We then define the loss function using cross-entropy loss, which is appropriate for classification problems. Finally, we set up a stochastic gradient descent optimizer with a learning rate of 0.1 so it can update the model's parameters during training. To train the model, we first switch it to training mode so gradients are computed. Then reset the optimizer's gradients to remove any leftover values. We feed the training data through the model to get logits, which are the raw prediction scores, and compare them to the true labels using cross-entropy loss. We then compute gradients of this loss with respect to the model's parameters, and finally let the optimizer update those parameters using the gradients to reduce the loss. To measure how strong the gradients are after a training step, we first set a running total to 0, then loop over all model parameters. For each parameter that has a gradient, we compute the norm of that gradient and add it to the total. The final value tells us the overall magnitude of the gradients, which reflects how much the model's parameters are being updated. After each training step, we print the loss as a floating point number to see how well the model is doing after that update. We then compute the gradient norm by adding up the norms of all parameter gradients, which tells us how large the parameter updates are. Finally, we print this gradient norm, rounded to 4 decimal places, to check that the gradients have a reasonable scale and are not too large or too small. Switching a model to evaluation mode tells it to perform inference instead of training. In this mode, certain layers, such as dropout and batch normalization, change how they behave, so they function properly during evaluation. This adjustment helps the model produce stable, consistent outputs when making predictions on new data. The model first runs on the validation data to produce predictions, which are then compared to the true validation labels using a loss function. This loss value tells us how well the model performs on unseen data. In this setting, we keep gradient tracking turned on for the loss, not to update the model immediately, but to study how the loss behaves when gradients are available. For this reason, we do not use a context that disables gradient computation during validation here. We check whether the validation loss needs gradients by looking at its requires gradient attribute. This tells us if the computation graph is still tracking operations for gradient calculation. Knowing this helps us understand whether the model is behaving in training mode, where gradients are needed, or in evaluation mode, where they usually are not. To evaluate the model on the validation set, we first turn the logits into predicted class labels by taking the position of the largest value for each sample. We then compare these predicted labels with the true labels to see which predictions are correct. This comparison is converted into ones and zeros, and we take the average of these values to obtain the validation accuracy as the proportion of correct predictions. Finally, we convert this accuracy into a standard Python float so it is easy to read and use later. We print the validation accuracy that was computed while gradients were being tracked, rounding it to 3 decimal places for clarity. This shows how accurate the model's predictions are during evaluation under gradient tracking. Doing this is useful for debugging and for better understanding the model's performance. During inference, we turn off gradient tracking using PyTorch's nograd feature to save memory and speed up computation. Within this context, we feed the validation inputs into the model to get the output logits. We then compute the validation loss from these logits and the true labels without recording gradients. Finally, we obtain the predicted classes by taking for each sample the position of the largest logit value, giving us the model's predictions without any gradient computation. To measure our model's accuracy, we first turn off gradient tracking and compare its predicted labels with the true validation labels to see which ones match. This comparison gives us a tensor of ones for correct predictions and zeros for incorrect ones. We then take the average of these values to get the proportion of correct predictions, which is the accuracy. Finally, we convert this result into a standard Python float so it is easy to read and use elsewhere. We check whether the validation loss requires gradients while using the no gradient context. This shows that the loss is computed without tracking operations for backpropagation. Running evaluation in this mode avoids unnecessary gradient calculations. This makes the evaluation step more efficient while keeping the model's behavior the same. We report the validation accuracy that was calculated inside a no gradient context, which means the system does not track gradients during evaluation. This makes validation more memory efficient and faster. For clear and precise reporting, the accuracy value is rounded to 3 decimal places before being printed. This code shows how using the no-grad context in PyTorch during inference can save memory by turning off the computation graph. This is especially helpful during evaluation when gradients are not needed and tracking them would waste resources. The print message explains that safe inference relies on this no-grad mode to make evaluation lighter and more efficient in terms of memory and computation. This script shows how to use PyTorch's no-grad context for safe and efficient inference by contrasting training and evaluation. A simple neural network is first trained on a small dataset using stochastic gradient descent, and the presence of gradients is confirmed by checking their norm after a training step. The model is then switched to evaluation mode, and validation is run twice, once with normal gradient tracking and once inside the no-grad context. In the first case, the validation loss still requires gradients, while in the no-grad case it does not, which saves memory. The script reports training loss, gradient norm, and validation accuracy in both scenarios, demonstrating that using no-grad makes evaluation lighter without changing accuracy. Accuracy and F1 metrics. Accuracy is a common first choice for evaluating training workflows, especially in classification, because it measures the fraction of correct predictions and is easy to explain to non-technical stakeholders. It compares predicted classes to the true classes and reports how often the model is right. However, accuracy can be misleading when the classes are imbalanced, meaning one class appears much more often than others. This situation is common in areas like fraud detection or rare disease diagnosis, where a model can achieve high accuracy by mostly predicting the majority class while still performing poorly on the rare but important cases. When working with imbalanced datasets, accuracy alone can be misleading, so it is important to use precision, recall, and the F1 score. Precision tells you what fraction of the cases predicted as positive are actually correct, while recall tells you what fraction of all true positive cases the model successfully finds. The F1 score combines precision and recall into a single measure, balancing the need to catch true positives with the need to avoid too many false alarms. In settings like medical screening, a model with a higher F1 score can be more useful than one with only high accuracy, because it better ensures real cases are detected without an excessive number of incorrect positive results. When adding accuracy and F1 to your training loop, compute them in a consistent way and interpret them based on your task and data distribution. During evaluation, collect all predictions and true labels across batches. Then calculate the metrics on this combined set for a clearer view of performance. Choose whether to report metrics per class or use averaged versions like macro or weighted F1, depending on what matters most. For example, in content moderation, you might track overall accuracy for general behavior and per class F1 to ensure harmful content is reliably detected and not misclassified. By carefully selecting and monitoring these metrics, you can turn raw model outputs into useful guidance for model selection and tuning. Python code, accuracy, and F1 metrics. This script demonstrates how to compute accuracy and F1 metrics while evaluating a model. It uses TensorFlow to simulate a typical evaluation workflow. The main goal is to calculate these metrics safely, making sure that no gradients are tracked during the process. This keeps the evaluation focused on measuring performance rather than updating model parameters. The line starting with an exclamation mark is a shell command that installs TensorFlow version 2.20.0 rather than being Python code. It makes sure that this exact version of TensorFlow is available before the script runs. Specifying the version is important because different TensorFlow versions can change features or behavior. By fixing the version, you help keep the environment consistent and avoid compatibility problems. We start by importing 3 key libraries. The operating system library lets us interact with the system, such as working with files or environment settings. The random library provides tools for generating random numbers and performing random operations when we need variability. Finally, the numerical computing library NumPy allows efficient handling of arrays and fast mathematical operations on large datasets. We begin by importing TensorFlow, a library used to build and train machine learning models. Within TensorFlow, we use Keras as a high-level interface that makes creating neural networks easier. We also import the Layers module from Keras so we can assemble key components of a network, such as convolutional and dense layers. Together, these imports provide the basic tools needed to construct and train our model efficiently. We set a seed value, such as 42, to make random operations reproducible, so we get the same results every time we run the code. We apply this seed to the standard random module, to the random number generator in NumPy, and to TensorFlow's random number generator. Doing this ensures that any random numbers, including those used to initialize neural network weights, are consistent across runs. This consistency is important for debugging and for fairly comparing results between different experiments. This line displays the version of TensorFlow currently being used in the script. It provides a quick check that the intended version of the library is installed and active. Confirming the version helps ensure compatibility with your code and makes debugging easier when something does not work as expected. The code uses TensorFlow tools to check whether any physical GPUs are available on the system. It lists all GPU devices and then evaluates if this list is non-empty. If at least one GPU is found, it chooses the GPU as the device for running the model. Otherwise, it falls back to the CPU. This approach automatically selects the best available hardware to help optimize model performance. This code checks whether a graphics processing unit is available and then prints which device will be used for computations. If a graphics card is detected, it selects the GPU. If not, it falls back to the CPU. The printed message lets you know whether your calculations will benefit from GPU acceleration or will run on the regular processor instead. We begin by loading the MNIST dataset using the Datasets module in Keras. MNIST is a standard machine learning benchmark made up of images of handwritten digits. The data is divided into training images and labels, and separate testing images and labels. We train the model on the training portion and then evaluate it on the testing portion to check how well it generalizes to new, unseen data. For this quick demonstration, we work with a smaller subset of the data. We choose 2,000 samples for training and 500 samples for testing. We then restrict the training data to the first 2,000 entries and adjust the corresponding labels so they match this reduced training set. This lets us illustrate the process without using the full dataset. For evaluation, we work with a smaller subset of the test data instead of the full set. We do this by selecting only the first few test images and their matching labels. Using this limited sample makes the evaluation faster and easier to manage. This approach is especially helpful for quick demonstrations or initial testing. To prepare the images for a neural network, the training images are first converted to floating point numbers, and then each pixel value is divided by 255. This rescales all pixels to fall between 0 and 1, which is a standard pre-processing step to keep inputs on a consistent range. The same conversion and normalization are applied to the test images. Using the same scaling for both training and test data is important for fair and accurate model evaluation. We expand the dimensions of the training and test datasets by adding a new axis at the end to create a channel dimension. This step is required because convolutional layers in a neural network expect input data with channels. By adding this axis, each image is treated as having a single channel, like a grayscale image. This ensures the data format matches what convolutional neural networks need for proper processing. Before building the model, the code first checks that the number of training images matches the number of training labels so that every image has a correct label. It performs the same check for the test images and test labels. These checks ensure that both the training and evaluation datasets are consistent and properly aligned. We build a small convolutional neural network in Keras for classifying grayscale digit images. It starts with a two-dimensional convolutional layer with 8 filters of size 3 by 3 and a ReLU activation, taking images that are 28 by 28 pixels with one channel. A 2 by 2 max pooling layer then reduces the spatial size of the feature maps. and the result is flattened into a one-dimensional vector. This vector feeds into a dense layer with 32 units and ReLU activation, followed by a final dense layer with 10 units and a softmax activation that outputs class probabilities for the digits 0 through 9. The model is now being compiled, which prepares it for training. It uses the Atom Optimizer, a common and efficient choice for updating weights, especially with sparse gradients. The loss function is sparse categorical cross-entropy, which is appropriate for multi-class classification when the labels are given as integers. During training, the model will also track accuracy, so we can monitor how well it is learning to make correct predictions. The model is trained using a fit function that takes the training data and their labels as input. Training runs for 2 epochs, meaning the model goes through the entire dataset twice. The data is handled in batches of 64 samples at a time. The verbosity is set so that no progress messages are printed, making this a quick, silent training setup suitable for a simple demonstration. To evaluate the model, we first use TensorFlow's data tools to build a dataset from the test images and their labels. We then group this dataset into batches of 64 samples. Batching allows the model to process many examples at once, making evaluation more efficient. During this step, we do not shuffle the data, so the evaluation follows the original order of the test set. To calculate accuracy from model predictions, we compare each prediction to the true label and count how many match. This count represents the number of correct predictions. We then determine the total number of predictions from the size of the true label set. Finally, we compute accuracy as the number of correct predictions divided by the total number of predictions, using a floating point value for precision. We define a function that computes precision, recall, and F1 scores for each class and then averages them. For every class, we count true positives where predictions and true labels both match the class, false positives where only the prediction matches, and false negatives where only the true label matches. Precision is true positives divided by true positives plus false positives, and recall is true positives divided by true positives plus false negatives, each with a tiny constant added to avoid division by 0. The F1 score for each class is then calculated as a harmonic mean of precision and recall, again with a small constant added. We store all class F1 scores in a list, and finally return the macro F1 score as the average of these values. We begin by running the model in evaluation mode without computing gradients, which makes inference more efficient. We then create 2 empty lists, one to collect the model's predicted labels, and another to store the true labels from the test set. By filling these lists, as we process the data, we can later compare predictions with actual outcomes. This comparison allows us to compute performance metrics, such as accuracy and the F1 score. We loop through each batch of images and labels from the validation set, and run the images through the model in inference mode so the model's weights stay fixed. This produces logits, which are the raw scores for each class. For each image, we pick the class with the highest score using an argmax operation and store these predicted classes. We also store the true labels from each batch. By collecting all predictions and all true labels across the entire validation set, we prepare the data needed to evaluate the model's performance. After evaluation, the code gathers all prediction and label arrays from the different batches and merges them into single continuous arrays. It does this using a numerical library function that concatenates the list of arrays along the first dimension. This step ensures that all predictions and labels share a consistent format. With this unified structure, it becomes straightforward to compute metrics such as accuracy and F1 score for the entire dataset. The code verifies that the arrays containing all predictions and all true labels have the same shape. This means every predicted label is paired with a corresponding actual label. Ensuring this one-to-one match is essential for computing evaluation metrics correctly. By enforcing this condition, the code avoids mismatches that could lead to inaccurate assessments of model performance. The code evaluates how accurate the model is on the validation data by calling a compute accuracy function with the true labels and the model's predicted labels. This function calculates the proportion of predictions that are correct and returns that value. The result is stored as the validation accuracy. This measurement is essential for judging how well the model performs on data it has not seen during training. To compute the macro F1 score for the MNIST digit classification task, we treat the 10 digits as 10 separate classes. We then use a function that takes the true labels, the predicted labels, and the number of classes as inputs. This function calculates the F1 score for each individual class and then averages these values. The result is the macro F1 score, which gives a balanced measure of the model's performance across all classes. We first report the validation accuracy, which is the fraction of labels the model predicts correctly. We then report the validation macro F1 score, which averages the F1 scores for each class to reflect a balanced view of precision and recall across all classes. Finally, we compute and print the difference between the macro F1 score and the accuracy to reveal any gap between overall correctness and class-wise balance. Together, these metrics show both how often the model is right and how fairly it performs across different classes. This script shows how to evaluate a simple convolutional neural network on a subset of the MNIST dataset using TensorFlow. It sets up a deterministic environment for reproducibility, checks for GPU availability, and briefly trains a basic convolutional model on a small portion of the data. After training, it evaluates the model on a test subset by computing accuracy and the macro F1 score. Accuracy reflects overall prediction correctness, while the macro F1 score balances precision and recall across all digit classes. The script then prints these metrics to highlight how well the model balances precision and recall, using only safe, gradient-free computations focused on evaluation. Devices and mixed precision. Moving data to CUDA. When training deep learning models, it is essential that both the model and the data are on the same device, typically a GPU. The GPU has its own memory separate from the CPU, so if the model is on the GPU but the data is not, each forward pass will trigger slow data transfers and create a bottleneck. To avoid this, move the model to the GPU once. Then for every batch, move the input tensors and labels to the GPU before running the forward pass. This practice is key for efficient training in applications such as medical imaging and language models. When training on a GPU, all tensors in each batch, including inputs, labels, and any metadata, must be on the same device as the model. If some tensors remain on the CPU, you can get errors or hidden data transfers that slow training. This is especially important for complex datasets that mix different data types, such as images and text. To avoid problems and use the hardware efficiently, adopt a consistent practice of moving every tensor to the correct device as soon as it is loaded, and make this a standard part of your training loop. When using CUDA, data transfers between the CPU and GPU are slower than computations on the GPU, so you should minimize how often data moves across this boundary. In large training tasks, such as recommendation systems or vision models, excessive transfers can significantly slow everything down. A good practice is to move each batch to the GPU once, perform all needed computations there, and only bring results back to the CPU when truly necessary. This disciplined approach makes your training process more efficient and easier to optimize further. Python code, moving data to CUDA. This script demonstrates how to move data onto different devices during training. It uses TensorFlow to imitate how CUDA would place data and computations on hardware. The main goal is to show safe, device-aware training so that operations run on the intended devices without errors. The line that starts with an exclamation mark is a command to install TensorFlow version 2.20.0. It is commonly used in environments such as Jupyter notebooks. The purpose is to make sure that this exact TensorFlow version is available so the script can run correctly. This helps maintain compatibility with the code that depends on TensorFlow's features and functions. We begin by importing a few key libraries needed for our work. The operating system library lets us interact with the computer's operating system. The random library gives us tools to generate random numbers and make random choices. Finally, we import NumPy, a numerical computing library that helps us work efficiently with arrays and perform mathematical operations. We start by importing TensorFlow, the main library we use to build and train machine learning models. After that, we print the TensorFlow version currently installed. Checking the version helps confirm compatibility and ensures we are working with the expected setup for our code and experiments. To make experiments reproducible, we set a fixed seed value so that random operations give the same results every time the code runs. We first sent the seed for Python's built-in random module, then for NumPy's random number generator, and finally for TensorFlow's random number generator. Using the same seed across these libraries ensures that all random numbers and operations stay consistent between runs. This is especially important when training machine learning models, so results can be reliably compared and repeated. We begin by checking whether any physical GPUs are available using TensorFlow's configuration tools, which list all detected GPU devices. From this list, we determine a simple yes or no answer about GPU availability. We then print this result, so we immediately know if GPU acceleration can be used for computations in the current session. The code first checks whether a GPU is available. If it finds one, it selects the first GPU as the computation device. If not, it falls back to the first CPU. This choice controls where all calculations will run, using the GPU for better performance when possible. Finally, it prints which device is being used, so you know what hardware is running the computations. We begin by creating a small synthetic dataset on the CPU with 64 samples and 8 features. Using a random number generator from a numerical library, we fill an array of this size with values drawn from a normal distribution. We then convert this array to the float32 data type, so it is compatible and efficient for use in TensorFlow operations. We start by creating a simple linear target vector on the CPU. The true weights are defined as a sequence of numbers from 1 up to the number of features, stored as 32-bit floating point values. We then compute the target values by multiplying the input data matrix by these true weights and adding 0.5 to each result. This produces target values that follow a clear linear relationship with the input features, mimicking a situation where outputs depend linearly on inputs. We first convert the input data from a NumPy array into a TensorFlow tensor so it can be processed efficiently, including on GPUs. We then apply the same conversion to the target data. By turning both the input features and target values into TensorFlow tensors, we ensure they are in a compatible format for TensorFlow operations. This makes it straightforward to feed the data into the model training pipeline. Before training begins, the code first checks that the input and target tensors contain the same number of samples, so that every input has a matching target value, which is essential for supervised learning. It also confirms that the input tensor has the expected number of features. These validation steps help catch shape mismatches early and prevent errors during model training. Within the selected device, we build a simple model using the Keras sequential interface in TensorFlow. The model takes input data with a number of features specified by a variable and passes it to a dense layer with a single output unit. This structure corresponds to a basic linear regression model, where the dense layer learns a linear mapping from the input features to the output. By choosing the device context, we ensure that all model operations run on the designated GPU or CPU to make efficient use of available hardware. The model is set up for training using the Atom optimizer, which is widely used in deep learning because it adjusts the learning rate automatically. It uses mean squared error as the loss function, a standard choice for regression problems. Together, these choices define how the model updates its weights and how its performance is measured during learning. The code checks whether a GPU is available to decide if mixed precision should be used during training. Mixed precision speeds up training by using lower precision data types when possible, which is especially useful on GPUs. After making this decision, the program prints a message indicating whether mixed precision will be used in the training process. We first check whether mixed precision should be used by seeing if the GPU setting is enabled. If it is, we import the mixed precision tools from the Keras part of TensorFlow and create a policy that uses mixed float 16 precision. We then set this as the global policy so that all later model operations follow this mixed precision strategy. Using this approach can greatly improve computational efficiency on supported hardware by using lower precision where it is safe to do so. We build a small dataset using TensorFlow's data tools by slicing tensors into features and targets. This approach lets us organize the inputs and outputs clearly for model training. Using the Data API also makes it easy to apply efficient operations like batching and shuffling. As a result, the training process can handle the data more effectively and at scale. The dataset is first shuffled using a buffer as large as the dataset itself, so that the samples are thoroughly mixed, which helps reduce bias from any fixed ordering. A seed value is used during shuffling so that the same random order can be reproduced in future runs. After shuffling, the data is split into batches of 16 samples. Batching allows the model to process several samples at once, making training more efficient and better suited to modern hardware, such as GPUs. We define a training step function that is optimized by TensorFlow for faster execution and runs on the selected device, such as a GPU or CPU. Inside this function, a gradient tape records the operations needed for automatic differentiation. The model generates predictions for a batch of inputs, and we compute the mean squared error between these predictions and the true values. Using the gradient tape, we calculate the gradients of this loss with respect to the model's trainable parameters and apply them with the optimizer to update the model. The function then returns the resulting loss value. We run a training loop for 3 epochs, and in each epoch we track the loss values for all batches. For every batch, we call the training step with its features and targets, obtain the batch loss, convert it to a float, and store it. After all batches in that epoch are processed, we compute the average of these losses to get the mean loss for the epoch. We then print the epoch number and this mean loss rounded to 4 decimal places to monitor how training is progressing over time. We begin by taking the first batch from the dataset iterator, which provides one tensor for inputs and another for targets. We then move these tensors onto the selected hardware device, such as a graphics processor or a central processor, depending on what is available. To do this, we use TensorFlow's identity operation to ensure the tensors are actually copied to that device. This step confirms that our data is correctly placed on the intended hardware, which is important for achieving good performance during training. We first check and print which device holds the input data to confirm it is on the intended processor, such as a GPU or CPU. We then do the same for the target data to make sure it is on the same device as the inputs. Finally, we check where the model's trainable variables are stored. Verifying that both the data and the model parameters are on the same device ensures consistent placement and efficient computation during training. This script shows how to move data and training to a GPU in TensorFlow for device-aware training. It checks whether a GPU is available, creates a synthetic dataset on the CPU, converts it to tensors, and builds a simple linear model with mean squared error loss. When a GPU is present, it enables mixed precision to improve performance, then shuffles and batches the data and runs a custom training step on the selected device for 3 epochs, reporting the mean loss. Finally, it explicitly moves a data batch to the chosen device to confirm that both the data and the model variables are located on the same device, ensuring efficient use of GPU resources when available. Automatic mixed precision. Automatic mixed precision speeds up training and reduces memory use by running many operations in lower precision while keeping important ones in full precision. Modern GPUs and deep learning frameworks work together to decide which calculations can safely use fewer bits and which must stay high precision for accuracy. Your forward pass and loss computation are wrapped so that precision is managed automatically, without you manually changing tensor types. This gives significant performance gains without requiring changes to the overall structure of your training code. Automatic mixed precision lets the framework run most model computations in lower precision during the forward pass, then switch back to higher precision when needed for tasks like gradient accumulation and weight updates. This works especially well for workloads such as medical or satellite image processing, where many operations can safely use half precision on specialized GPUs to increase throughput and save memory. At the same time, numerically sensitive operations, including softmax and loss reductions, are kept in full precision to preserve accuracy. The mixed precision engine manages these choices automatically, so you typically just enable it with a simple configuration change to get faster training with similar model quality. Automatic mixed precision can speed up training, but you must watch its impact on accuracy and reproducibility. Because some values use fewer bits, small numerical errors can accumulate and affect convergence, especially in models that are already numerically fragile. When you first enable mixed precision, compare loss curves, validation metrics, and gradient norms against a solid full precision baseline. In sensitive domains like finance or scientific simulation, you may keep critical operations in full precision if you see instability. Over time, as you learn how your models and datasets behave, you can choose a balance between performance gains and numerical reliability. Python code, automatic mixed precision. This script demonstrates how to use TensorFlow's automatic mixed precision feature. It compares training a model on the MNIST dataset using standard float 32 precision versus mixed precision. The main goal is to show how mixed precision can safely improve performance. It also highlights the role of different devices in achieving these performance gains. The line with the exclamation mark is a command to install TensorFlow using the pip package manager. It is normally run in a terminal or notebook to make sure TensorFlow is available for the script. In this case, it is commented out, which suggests the script expects TensorFlow to be already installed, or that the user will run the installation command separately if needed. We begin by importing a few key libraries that we will use throughout our work. The operating system library lets us interact with the system for tasks like managing files and environment settings. The random library provides tools for generating random numbers, which is useful for things like setting scenes, so results can be reproduced. Finally, the numerical computing library NumPy gives us efficient support for working with arrays and performing mathematical operations. We start by importing TensorFlow, a powerful library for machine learning and deep learning, and Keras, its high-level interface that makes it easier to build and train neural networks. We also bring in the Keras Layers module, which provides essential components like convolutional, pooling, and dense layers. Together, these imports give us the core tools needed to design, construct, and manage neural network models efficiently. We set a seed value of 42 so that our results are reproducible. We first apply this seed to the standard random library, then to NumPy's random number generator, and finally to TensorFlow's random number generator. Using the same seed across these libraries makes all their random operations consistent from one run to the next. This deterministic behavior is important for debugging and for fairly comparing model performance. The script first reports the TensorFlow version so you can confirm it matches the features you plan to use. It then checks whether a graphics processing unit is available by listing physical devices and seeing if that list is empty. If at least one device is found, it confirms that a GPU is present. This information is important because having a GPU allows you to use hardware acceleration during model training. The code uses a Keras tool to load the MNIST dataset, which is a standard collection of handwritten digit images for training image recognition models. It automatically splits the data into a training set with images and their labels used to teach the model, and a test set with separate images and labels used only for evaluation. This separation is important because it lets us measure how well the trained model performs on new, unseen data. To speed up the demonstration, the code uses a smaller portion of the MNIST dataset instead of the full data. It selects the first 8,000 images and labels from the training set, and the first 2,000 from the test set. By working with this reduced subset, it becomes faster and easier to experiment with the model and evaluate its performance. The code first converts the training and test images to 32-bit floating point numbers so they work properly with TensorFlow operations. It then normalizes the pixel values by dividing them by 255, which scales them into a range from 0 to 1. This standardized input range helps stabilize and improve the model's training process, making it easier for the model to learn from the image data. To prepare image data for convolutional layers, we need to add a channel dimension to each image. We do this by using a function from the numerical library that expands the array along the last axis. So each image is reshaped to include a single channel. This step is required for convolutional operations to work correctly. We apply the same transformation to both the training and test data so their input shapes remain consistent during training and evaluation. Before building the neural network models, the code first checks that the training and test images have the correct shape for the input layer. It confirms that each image is 28 pixels high, 28 pixels wide, and has a single channel, as expected for grayscale data. This verification step ensures the images are properly formatted so the convolutional layers can process them correctly. We define a simple convolutional neural network for grayscale images of size 28 by 28 pixels. The model starts with an input layer, followed by a two-dimensional convolutional layer with 16 filters and ReLU activation, then a max pooling layer that downsamples the feature maps. A second convolutional layer with 32 filters and ReLU activation is added, and its output is flattened into a one-dimensional vector. This vector passes through a dense layer with 64 units and ReLU activation to learn more complex patterns. Finally, an output dense layer with 10 units and a softmax activation produces class probabilities for tasks like MNIST digit classification, and the model is returned for further use. We begin by creating a baseline model using a build model function that constructs a simple convolutional neural network to serve as our performance reference. This model runs on the default available device, which may be either a CPU or a GPU. It uses standard 32-bit floating point precision in TensorFlow, making it straightforward to compare later with versions that use mixed precision. We compile the baseline model using the Atom Optimizer, which is well suited for deep learning because it adapts the learning rate during training. The learning rate is set to 0.001, a common default that balances how fast the model learns with training stability. For the loss function, we use sparse categorical cross-entropy, which is appropriate for multi-class classification tasks like MNIST, where the labels are integer class indices. We also track accuracy as the main metric so we can monitor how well the model correctly classifies the data during training. The baseline model is trained using the standard Keras fitting procedure, which takes the training data and labels as input. 10% of the training data is held out for validation during training. The model passes through the entire dataset twice, meaning it is trained for 2 epochs. It uses a batch size of 64 samples per update, and the training runs silently because progress output is turned off. The baseline model is evaluated on the test dataset using Keras, which calculates its loss and accuracy on the test images and their labels. The evaluation is run in silent mode, so no progress messages are printed. The resulting loss and accuracy values are then stored for later use and analysis. The code first checks whether a GPU is available in TensorFlow. If a GPU is found, it sets a mixed precision policy that uses lower precision floating point numbers where possible to speed up computation on compatible hardware. If no GPU is detected, it instead uses standard single precision to maintain compatibility and stability on CPU-only systems. This global precision policy is then applied so that the entire training process automatically uses the most appropriate settings for the detected hardware. We now create a new model using the current mixed precision policy, which configures the network to train with mixed precision and can improve performance on supported GPUs. Calling the model building function constructs a fresh instance of our convolutional neural network architecture. This new model is now ready to be compiled and trained under the mixed precision settings. We first create an Atom Optimizer with a learning rate of 1,000th, then wrap it with TensorFlow's mixed precision loss scale optimizer. This wrapper adjusts the scale of the loss to better manage the dynamic range of gradients during training. By doing so, it helps avoid numerical instability that can occur when using mixed precision. This setup is important for safely gaining the performance benefits of mixed precision training on supported hardware. We now compile the model using mixed precision, which means the optimizer is specially wrapped to handle lower precision calculations during training. The loss function is sparse categorical cross-entropy, which is appropriate for multi-class classification tasks such as MNIST digit recognition. We also track accuracy as a metric to monitor how well the model is performing. With this configuration, the model is ready for training with mixed precision, which can improve performance on supported hardware. The code trains a mixed precision model on the training data while holding out 10% as validation to track performance on unseen examples. It runs for 2 epochs, so the model passes through the entire dataset twice. A batch size of 64 is used, meaning the model updates its weights after processing 64 samples at a time. The training is run in silent mode, with no progress messages printed during the process. The mixed precision model is evaluated on the test dataset using the Keras evaluate function, which takes the test inputs and their corresponding labels. During this process, detailed output is turned off, so the evaluation runs quietly. The function then computes the model's performance and returns two key metrics: the loss on the test data and the accuracy on the test data. These values are stored for later use and analysis. We compare a baseline model that uses standard float32 precision with a mixed precision model by printing their test accuracy and loss, each rounded to 4 decimal places. First, we report the test accuracy of the float32 model, then the accuracy of the mixed precision model to see if performance improves. We do the same for test loss, showing how well each model minimizes error. This side-by-side comparison of accuracy and loss helps us evaluate whether mixed precision offers benefits over standard float32 precision. This script shows how TensorFlow's automatic mixed precision can speed up training on the MNIST dataset. It first builds and trains a simple convolutional neural network using standard 32-bit floating point precision, then evaluates its accuracy and loss on test data. If a compatible GPU is available, it switches to a mixed precision policy that uses 16-bit floats for some operations to improve performance while keeping accuracy similar. A new model is trained under this policy, and the script compares the test accuracy and loss of the baseline and mixed precision models, typically finding comparable accuracy with faster training when mixed precision is used. Stable grad scalar usage. In mixed precision training, a gradient scalar is essential for numerical stability. It temporarily scales up the loss before backpropagation so that the resulting gradients are larger and less likely to underflow in lower precision. After the gradients are computed, the scalar reduces them back down before the optimizer updates the model. This scaling process is especially important on modern accelerators that rely heavily on half precision, because it prevents very small gradients in deep networks from becoming zero and stopping learning over time. A gradient scalar automatically adapts to your model and data during training. At each iteration, it checks the gradients for invalid values such as infinities that signal overflow. When it detects these, it skips the optimizer update and lowers the scale factor to reduce the chance of future overflows. If training proceeds without issues for several steps, it raises the scale factor to better use the available numerical range. This adaptive behavior lets you rely on the scalar's default settings for stable and robust training, even in complex situations. When using a gradient scalar in mixed precision training, make sure it is consistently applied throughout the training loop and that you understand its behavior. Skipped optimizer steps are normal, especially early in training or with complex models, and can signal issues such as an overly high learning rate or very large activations. Watching how often steps are skipped can guide adjustments to hyperparameters or data preprocessing. In a stable run, the scalar will gradually adapt to reduce overflows, preserving the speed benefits of mixed precision while maintaining model accuracy. Python code. Stable grad scalar usage. This script demonstrates how to use a stable gradient scalar in a mixed precision training setup with TensorFlow. It focuses on safely scaling gradients to maintain numerical stability while training. The example also highlights clear device placement, so you know exactly where computations are running. Overall, it serves as a concise guide to stable mixed precision training with proper scaling and device control. The line that begins with an exclamation mark is a command to install TensorFlow version 2.20.0. Specifying this exact version makes sure the script uses the expected features and behaves consistently. This helps avoid problems that might occur if a newer TensorFlow update changes how things work. In practice, fixing the version like this is a common way to maintain compatibility and prevent unexpected behavior. We begin by importing 3 key tools for our script. The operating system module lets us interact with the system, such as working with files or environment settings. The random module provides random number generation, which is useful for creating random data or setting random seeds. Finally, the numerical computing library NumPy gives us efficient support for arrays and mathematical operations. Together, these imports prepare our environment for data manipulation and reproducible computations. We begin by importing TensorFlow, which we use to build and train machine learning models. From TensorFlow, we then import Keras, a high-level interface that makes creating neural networks easier. Finally, we import the layers module from Keras, so we can define different parts of the network, such as fully connected dense layers. These imports provide the basic tools needed to define and train our model efficiently. We set the seed value to 42 so that any random operations in our code give the same results every time, which is important for reproducibility. We first set the seed for the standard random module so its random numbers are consistent. Then we set the seed for the NumPy random number generator to control randomness in NumPy operations. Finally, we set the seed for TensorFlow's random number generator so TensorFlow operations are also consistent. Using all 3 seeds together helps make the overall behavior of our program deterministic across these libraries. This line displays the version of TensorFlow currently being used in the script. It provides a quick check that the correct version of the library is installed and running. Confirming the version helps ensure compatibility and that all features and functions work as expected. We first ask TensorFlow to list all physical devices labeled as GPUs to see if a graphics processor is available. From this list, we create a simple true or false value that tells us whether any GPU was found. Using that result, we choose a device name that points to either the first GPU when one is available or the first CPU when it is not. This device name is then used later to run our computations on the most suitable hardware, taking advantage of GPU acceleration when possible. We first check whether a graphics processing unit is available, and only if it is, we import the mixed precision tools from the deep learning library. Mixed precision lets the model use both 16-bit and 32-bit floating point numbers to improve performance. We then create a mixed precision policy that specifies this mixed float road and set it as the global policy. After this, all model operations will use mixed precision whenever possible. To begin, we create a small synthetic regression dataset with 256 samples and 8 input features. We generate random values for these features using a numerical library that produces arrays with the desired shape. Finally, we set the data type to 32-bit floating point numbers so the dataset is compatible with TensorFlow operations. We start by defining the true weights as a sequence of floating point numbers from 1 up to the number of features, which act as the coefficients in our linear model. We also set a true bias term of 0.5, which will be added to the weighted sum of the inputs. Then we compute the target values by multiplying the input data by the true weights and adding the bias. This process creates a simple linear relationship between inputs and targets that we will use to train the model. To make our synthetic data more realistic, we add a small amount of random noise to it. We generate this noise with a numerical random number generator, scale it by a factor of 0.1, and keep it in the same floating point format as the rest of the data. We then add this noise to the target values, which introduces variability similar to what we would see in real-world data. Before building the dataset, the code first checks that the input and target data have the correct shapes. It confirms that the input data is organized as a certain number of samples, each with a fixed number of features, matching the model's expected structure. It also verifies that the target data has one value per sample, matching the expected output format. These checks help detect mismatches early and prevent errors during model training. We begin by choosing a batch size of 32, which controls how many training samples are processed together at once. Then, we build a TensorFlow dataset from our input features and target values so they can be iterated over efficiently. We shuffle this dataset using a buffer the size of the full dataset and a fixed random seed, so the samples are mixed well while still allowing reproducible results. Finally, we group the shuffled data into batches of the chosen size, making the training process more efficient and manageable. We build a simple sequential regression model in Paris, placing it on a GPU if available to improve performance. The model has two dense layers. The first has 16 units with a ReLU activation to introduce nonlinearity and learn complex patterns, and its input shape matches the number of features in the data. The second layer has a single unit that produces the final continuous output value. This structure is a common and effective setup for basic regression tasks. We configure our model by choosing the Atom optimizer, which efficiently handles sparse gradients and adapts the learning rate during training. In this setup, the learning rate is set to 0.01, controlling how strongly the model's weights are updated based on the gradient. We also select mean squared error as the loss function, a common choice for regression tasks. This loss measures how well the model's predictions match the targets by averaging the squared differences between them. We only create a gradient scalar when we use mixed precision, which depends on whether a GPU is available. If a GPU is present, we set up the scalar with TensorFlow's mixed precision loss scale optimizer and pass in the optimizer. This scalar adjusts the size of gradients to reduce numerical problems during training. If there is no GPU, we do not use mixed precision and simply leave the scalar unset. We define a training step function and use TensorFlow's function decorator to make it run efficiently. Inside this function, we use TensorFlow's debugging tools to check that the shapes of the inputs and targets are what we expect. The inputs should have some number of rows with a fixed number of features, and the targets should have the same number of rows. These checks help catch shape mismatches early and prevent runtime errors during training. During training, we first check whether a scalar is available, which means mixed precision is being used. With a gradient tape, the model makes predictions in training mode. We compute the loss between targets and predictions, then scale this loss for numerical stability. We compute gradients of the scaled loss, unscale them, and use the scalars method to apply these gradients and update the model's weights, finally returning the original loss. If no scalar is present, we follow the same overall process, but without scaling. We record operations with a gradient tape, get predictions, compute the loss, calculate gradients directly, apply them with the optimizer, and return the loss. We define a function to evaluate the model without tracking gradients, which is useful during validation or testing. This function is optimized with TensorFlow's function decorator for faster execution. Inside it, we run the model in inference mode by turning off training and generate predictions. We then squeeze the predictions to match the target shape, compute the loss between targets and predictions, and return this loss as a measure of how well the model performs on the given inputs. We run a training loop for 3 epochs, and in each epoch we keep track of the loss for every batch. At the start of an epoch, we create an empty list to store these loss values. We then go through the dataset batch by batch, and for each batch, we call the training step function with its inputs and targets. This function performs one training update and returns the loss for that batch, which we add to our list. By collecting these losses, we can monitor how the model performs over the entire epoch. To get the mean loss for an epoch, we apply TensorFlow's reduce mean operation to the list of losses from all batches. This operation computes the average of those batch losses. The result is a single numeric value that summarizes the model's overall training performance for that entire epoch. After each training epoch, the model is evaluated on the full dataset using a separate evaluation step. This step takes the inputs and their targets, then computes the loss without tracking gradients. Because gradients are not tracked, this loss reflects performance without affecting the model's parameters. The resulting evaluation loss is used to judge how well the model generalizes to data it was not just trained on. The code reports a brief summary of training after each epoch. It prints the epoch number along with the average training loss and the evaluation loss for that epoch. This lets you quickly see how the model's performance is changing over time and how well it is learning from the training data while generalizing to the evaluation data. This script shows how to use mixed precision training in TensorFlow with stable gradient scaling. It first sets up a deterministic environment for reproducible results, then checks for a GPU, and applies a mixed precision policy when one is available to improve performance. A simple synthetic regression dataset is generated, and a small sequential neural network is trained with the Atom optimizer. When mixed precision is active, a gradient scaler is used to keep training numerically stable. The model is trained for 3 epochs, with training and evaluation losses reported each time, illustrating how mixed precision can boost efficiency and stability, especially on GPUs. In this lecture, you learn to implement a standard PyTorch training loop that iterates over DataLoader batches and updates model parameters. Add evaluation and metric computation to the training workflow without leaking gradients or mixing modes. And handle device placement and optional mixed precision to improve performance while maintaining correctness. In the next module, Module 4, we will go over data and data loaders. Thank you for your attention. See you all in the next lecture.